Well, thank you very much. It's a pleasure to be here. I'm Grant Passmore, and my co-founder, Denis Ignatovich, is here in the audience. Thank you to Vitalik for the invitation. So we're going to talk to you today about our formal verification platform, Imandra, and in particular, something we're calling Imandra contracts, which is the application of Imandra to Ethereum smart contracts, both to analyze smart contracts, reason about them, be able to prove properties of them, compute proofs and counterexamples, and then on top of that, to actually do risk management. So I'll tell you what I mean, but for those in investment banking, we mean, compute Greeks and so on. So let me start with a video that gives you a background on what we're doing at Aesthetic Integration. Let's see if the sound, I'll start it over, here we go.
What's plaguing today's electronic financial markets? The world economy is built on a staggeringly complex tangle of outcomes. Competitive pressures and economic recession contribute to increasingly opaque and unstable markets. The effects of legitimate unfair advantages can be devastating, cratering the confidence of investors and ultimately hurting the general public. Regulators and the industry have worked tirelessly to define what safe and fair markets are. What's been missing is a way to analyze and regulate all the algorithms underlying. The solution is formal verification, the science of correct algorithms. Other safety critical industries already rely on formal verification to make their algorithms safe. Devcon, by Aesthetic Integration, is the world's first formal verification solution for financial markets. Consider the building of a bridge. A design flaw may be catastrophic. To make it safe, engineers use powerful computer-aided design tools which analyze designs for safety automatically. Powered by latest advances in artificial intelligence, computer science, and mathematics, Imandra brings unprecedented rigor to the electronic financial markets, analyzing the safety and fairness of algorithms before they're deployed. Financial algorithms are unfathomably complex. They can be in a virtually infinite number of possible states. Examining 1,000 or even 100,000 test cases isn't enough. We must consider every possible case and answer definitively what can possibly go wrong. Imandra allows designers and regulators to fix breaches of safety and fairness before they affect markets. Let's build a safer, more reliable, and regulatory compliance system that all users can trust, saving everyone time and money. Imandra, by Aesthetic Integration, the logic of financial risk.
All right. So that gave you a bit of an overview of what we're doing at Aesthetic Integration. The big idea is we're bringing the hard science of formal verification, techniques that are relied upon already in safety-critical industries like avionics and hardware design, finally to finance, so that financial algorithms, things like dark pool matching logics, exchange matching logics, market-making algorithms, smart order routers, the type of algorithm that is really at the heart of our global financial infrastructure, so that they can actually be analyzed rigorously and reasoned about. So a bit of our background. So Denis formerly was the head of the Central Risk Trading Desk at Deutsche, roughly, I believe, 9 years at Deutsche. By the way, we were undergrad roommates in Texas. And then as Denis went to Wall Street, I went to academia, did my PhD in formal verification, in particular, the real algebraic geometry for reasoning about autopilot algorithms and being able to prove safety properties of autopilot algorithms in avionics and now in self-driving cars. And ended up as a postdoc at Cambridge while Denis was working at Deutsche. And we realized we were working in many ways on some of the same problems. He had very complex trading algorithms that constantly everyone was worried. If we commit a line of code, is this change all of a sudden going to cause us to violate a regulation? And it's very hard to get right if you think of modern market microstructure, something like an exchange, a trading venue in the US, for instance. It may have upwards of 20, 30, 40 different order types. And each of those order types, effectively, it's a way of packaging risk. It's a programming language. And as you introduce new order types, it's very difficult by hand to understand what can possibly go wrong. So when it comes to smart contracts, really, we have the same issues. So if I come to you and say, look, I promise, this piece of bytecode really implements fair escrow. Please send me your assets. How do you know? Likewise, if I say, I promise this implements a swap that we've agreed upon, how do you know? You can't ultimately trust the result or the design of a given smart contract without reasoning about it, without proving theorems about its possible behavior. So what we've done is we've taken our Imandra engine, which I'll tell you about, for reasoning about financial algorithms, and now we've adapted it in effectively two different ways I'll tell you about. One that's reasoning about a high-level language that can be compiled down to Ethereum bytecode, and the other that effectively is doing something called verified decompilation, that takes Ethereum bytecode, decompiles it to IML, our high-level functional language, that's actually a formalized subset of OCaml. If you know OCaml, allows you to reason about it and push the proofs back down to be proofs about bytecode. So, okay, that's reasoning about individual contracts. But as I mentioned, fundamental importance as a bank who's a pioneer right now with, let's say, Ethereum, as they're looking down the road 3 years from now. What happens when they have a portfolio of 100,000 smart contracts, right? You have to do risk management in the large. You have to compute Greeks. And to do that, you have to reason about the code. So you must have effectively formal semantics that ultimately is mechanized for reasoning about your smart contracts. So let me tell you a bit about how Imandra is used currently. So our biggest focus has been something we call Imandra venues. And this is using Imandra to formally analyze the matching logics behind trading venues, things like stock exchanges and dark pools. So you may have heard about many glitches in the past few years. For instance, BATS failed trading its own IPO. Of course, famous NASDAQ glitch with Facebook, Knight Capital, Goldman Sachs Alphabet trading glitch. These happen all the time in finance, and fundamentally what's been missing is a way to reason about the algorithms in advance of their deployment. So Imandra venues is now currently at use at top 5 global investment banks, effectively to take what is classically an imprecisely described algorithm, their collection of matching logic that is usually described, say, in some collection of PDFs. There is classically no formal spec of how these things are supposed to work, but it's actually taking those ambiguous, sort of imprecise specs, making them precise in Imandra, reasoning about fairness and safety properties, and then using Imandra to vet their high-performance production systems to ensure that the production systems really correspond to the verified specifications. So there's also some exciting developments we have in the regulatory space. So just to say, we came out of stealth mode with this in April, and the SEC brought us to Washington, D.C., to the SEC headquarters to teach them about Imandra for 2 days, and some exciting developments will be announced soon on Imandra in the regulatory space. But fundamentally, regulators face the same issues. Someone comes to them and says, I'd like to add this new order type to my trading venue. Ensure for me that this is allowed. And the SEC then has to process these things, and so does the FCA and other global regulators. And it's virtually impossible to do by hand without formal verification. So what is Imandra? I'm going to give you very low-level demos of Imandra. This is a very technical audience, so I want you to see really in action, and I want to talk to you a bit about the automated reasoning and mathematical logic that's under the hood. But fundamentally, it's 3 things in one. It's a programming language, so it's a formalized subset of OCaml, if you're familiar with OCaml in the ML family of languages, functional language. It's a mathematical logic, so fundamentally, every data type definition or every program that you define, every function you define in Imandra is automatically transformed into an axiomatic representation that then Imandra's reasoning engine reasons about. So you write code and questions that you would like to ask Imandra about your code, and Imandra works to produce proofs or counterexamples using many different types of decision procedures, and I'll talk to you more about that. So that's the big idea, what I just outlined. Effectively, you give Imandra your financial algorithm or your smart contract and ask Imandra a question. Is there a potential glitch of this class? Or does this do some concrete form of unfair trading? For instance, is there some sequence of messages that could be sent to this trading venue that could allow someone to jump the queue? right? And ultimately, you get out either that the algorithm is verified with a mathematical proof that can be independently vetted, or you get a counterexample. So that's the big idea, pushing these questions into what are called decidable fragments, so that this is automatic. So let me show you a very simple example. Here, we have on the left, if you can read it, a summation function just in Imandra. So this is just summing up the numbers from 0 to n, the natural numbers, and it's a program. So on the right, we're just computing with it, right? We can compute sum of 5, sum of 100. But you may remember this possibly apocryphal story of Gauss as a 6-year-old, proving actually that the sum of n, sum of 0 up to n is equal to n times n plus 1 over 2. So we can not only define programs, but we can write verification goals. And what we've done here is we've asked Imandra to actually verify this statement on the left. To verify, we named it Gauss. And we asked Imandra to prove for every possible input n, if n is greater than or equal to 0, then the sum of n is n times n plus 1 over 2. So Imandra then goes and does a proof by induction, and et cetera. We can see a trace of that proof. Great. Proof by induction, as you might do by hand, and ultimately has to do some symbolic rewriting. That proof can be exported, can be verified by an open source proof checker, so you don't have to trust it. But now, what happens more often, of course, is we have bugs in our code. So instead here, I've swapped a plus for a minus, right? And I'm asking Imandra instead to prove that sum of n is equal to something really that it's not equal to. And Imandra comes back and gives me a counterexample. So that's a super simple example. But let me show you something more complex. So I believe I don't have too much time. But for instance, here's an example where I'm effectively defining algebraic data types. And I'm asking Imandra to compute some complex counterexamples for me. And again, it comes back, and always the counterexamples it gives me, those are valid IML. They're valid OCaml objects. They can be reflected into the language and computed with. So this same idea now can actually be scaled to reason about financial algorithms. So for instance, we can take the design of a dark pool, which I have on the left here, fairly complex matching logic. This is of a global investment bank, top 5 investment bank's dark pool. And now we can reason about it. So by the way, this is all based on publicly available information, don't worry. So now, for instance, I can ask Imandra, is the order ranking function transitive, right? So that's something we really care about, a fairness property. So I can ask Imandra this question. It has a model of the matching logic on the right that's also a high-performance simulator. And Imandra comes back and synthesizes for me a counterexample. So now I have concrete values of different orders, effectively, that could exist in the book of this dark pool where the ranking function violates transitivity. So that's the main idea, proofs and counterexamples. So let me quickly cut to the chase for Ethereum. So what we've done here is we've taken Imandra and we've adapted it so that in IML, in this fragment of OCaml, you can directly write smart contracts. So there's many things to talk to you about how we actually do the compilation. So right now, we actually compile effectively your customized smart contract code via Serpent. We compile it first to Serpent, and we have different encoding mechanisms for how we encode algebraic data types recursively. But now we have this smart contract, let's say, for a crowdfunding example, and now we can ask Imandra to reason about it. So, for instance, we just had Imandra prove that in this smart contract, you effectively can't jump the queue in a certain sense. And then we ask another question, effectively, that we will always get our money back if we come in after a certain timeout, and Imandra computes for us a counterexample where that fails. So that's the big idea. I think I need to end here, but we have these different modes. Effectively, you can go IML directly to bytecode via Serpent, reason about your IML, or we can use our Ethereum to IML verified decompiler. So sign up, please, if you'd like to join the private alpha, and thank you very much.
So Dennis, you have 5 more minutes if you like. Sorry? 5 minutes.
Oh.
You want to?
I think okay. He said I was.
It's okay.
Oh, okay.
5 minutes.
Oh, okay. Well, that's okay. I mean, if there's any questions. Okay, yes.
So we can write So are you saying we can write smart contracts in OCaml now?
Exactly, in IML. So IML is not all of OCaml, but it's, you know, polymorphic Hindley-Milner fragment of OCaml. For instance, it doesn't support exceptions, so that's a fundamental difference. But instead of exceptions, you use, you know, things like option types. But yes.
That is pretty awesome.
Oh, thank you.
you.
But pardon me? It's not. It's not. So effectively, we have a reasoning as a service API. We have an online web interface, and we have an open source proof checker. So you can always, you don't have to trust the proofs. The hard part is finding the proofs. You know, the easy part is checking the proofs. So currently, it's not open source, though I'm sure we'll open source pieces of it over time. Yes?
Are you going to run your own source of this Imandra releasing action? Are you going to get a reasoning?
You mean use Imandra to reason about Imandra?
Yeah.
Yeah, it's a great question. So there's you know, sort of architecture of Imandra. There's some bootstrapping in Imandra that is not written in Imandra. That's written in, let's say, raw OCaml C. But then most of Imandra actually is written in Imandra after this bootstrapping. So we've actually done some self-verifications. I mean, you know, you always have these fundamental meta-mathematical results that if you want to prove ultimately consistency of your own system, you effectively need to add, you know, something like transfinite induction up to a larger ordinal. So actually, Imandra's logic, it's related to a logic called primitive recursive arithmetic of Skolem, but it's typed. But then we have transfinite induction up to an ordinal called epsilon 0. So basically, that means we can, you know, synthesize and do termination proofs of functions that, you know, effectively recurse in some complex ways. But, so what you would have to do, because we already have that strong ordinal in the logic, you'd have to add an induction principle up to a bigger ordinal. But you can, you know, so proof theorists have isolated effectively the ordinal analysis of theories like this. So you could do it and actually try to prove soundness properties of Imandra as a whole. But one of our really driving philosophies has been we always just want our proofs to be independently checkable as well. So when we produce a proof object, ultimately you can use a simple checker to check that proof object. Or if we produce a counterexample, it's an explicit, you know, value of a given type that you can run your system on. So in either case, you don't have to trust us. But we have a lot of ideas where, you know, we would love to talk to members of the community who are interested. A lot of ideas of effectively attaching this type of evidence directly to smart contracts, different ways that we can, you know, actually have an API where you can easily query what is known about this contract, what's been proved about it, what's been disproved. Also, you know, there are times you need to prove lemmas before Imandra will, you know, actually prove your main theorem. You know, happens all of the time for, let's say, you know, very deep properties. And there we imagine you could have, you know, sort of bounties where you want to give someone, you know, some number of credits if they prove this lemma for you that you relied upon. And so there's lots of cool things I think we can do community-wise.
My understanding of flash crashes is that they're either generated by fat fingers.
Flash crashes are either generated by fat fingers or like downward spirals where algorithms are forced to sell because other algorithms are selling. And so you just get this very, very quick negative spiral down. Like, how would Imandra help in either of those two cases?
Oh, it's a great question. I mean, fundamentally, there's a number of answers. So if you look at what is happening, so first of all, flash crashes happen a lot more often than, you know, we hear about in the press, right? These happened at a micro level. It is not uncommon. And a lot of work has been done effectively having things like specialized risk gates, specialized circuit breakers, that are effectively, you know, trying to act as an arbiter to make sure that things don't get out of control. So, for instance, some of our clients now, the first thing they actually do is they use Imandra to reason about their risk gate component. Before they go and reason, let's say they have an order router, before they start to reason about best execution of their routing, they may use Imandra first to prove that their risk gate component, which is just this last piece, that it effectively won't let something crazy out the door. So you can effectively incrementally verify these circuit breakers, these risk gates, get those safe first, and then start to verify more pieces that are, you know, more algorithmically interesting. So, did that answer your question? Okay, thank you very much.
Thank you, Dennis.
Sure.